I'm sorry, Eleanor. I'm sorry. I forgot to start. So I'm halfway through the review of the vector notes, which is chapter 3. They'll tell you that for the most part I've just been reading the slides, so it's kind of boring for them. I'm attempting as best as possible to get through this pretty quick. You can read through this. We are on slide. Slide is not. Hold on. So I'll fix that. We'll fix that real quick. What slide are we on? Where's the preview? Previews. Okay, so we're on 18. I think I'm going to go to slide about 30 or 40 here. It's going to, but I've been flying through them. I think I've been talking for what, like 5, 10 minutes? Not a ton of time. So anyway, so you can read through there to 18, but I'm going to continue from this point. All right, when adding vectors to all have the same units, all vectors must be the same quantities, boom. Okay, negative vectors. This is one we talked about a lot last year. Okay, it's going to become even more important right now. Okay, essentially the principle of, as you're looking right here, a negative is by definition what you add to a positive to make it 0. Okay, so visually, if that is A, what quadrant is B? What quadrant is negative A in? The third. It is the exact same size and just flipped 180 degrees. It is the opposite direction. And if you think about it, that's entirely what negatives have always been, even in scalar capacity as well, right? If you draw a number line, which I'm not going to do all the way out, but let's go, here's 0, here's -5, and here's +5, okay? There is +5. What is -5? The exact same size of arrow, 180 degrees the opposite way. All right. Yep. Okay. So, how do you subtract vectors? Literally just adding vectors is the exact same technique. The only difference is one of those vectors needs to be a negative vector. So you take the vector ahead of time, you flip it 180 degrees, and then you just do vector addition entirely like normal. Yeah, it's just subtracting vectors is just adding vectors with the one tweak at the very beginning of you'd flip one of them 180 degrees. Meaning, just real quick, if I have a vector A that I've used a bunch here, which is 10 meters at 53.1 degrees, okay? And I have vector B, which is, let's go, 5 meters at 90 degrees, okay? A plus B would look like this. There's A. I don't love that. I'm in the wrong spot. Let's go back. Erase. Erase. Nope, that's not the eraser. Erase. Where are you at? Eraser. Thank you. Eraser. Thank you. Okay. So if that is A, and that is B right there, okay, all you would do at the very beginning is take B like this and change its angle. What is its angle? What would would negative B's angle be? 270 or -90. So you take at -90 degrees or 270, whichever you want, and then instead of going up here, you would go down here. There's negative B, and there would be your final answer in that particular case. Make sense? Cool beans. It's going to get to component vector addition. Unless you want me to, I'm going to entirely skip component vector addition. Cool beans. All right, subtracting vectors from this other perspective. I think that's literally what I just said, so I'm not going to worry about it. Multiplying or dividing by a scalar. Okay, this is arguably new, but also not. You will see that we have actually already done this. The result of multiplication of or division of a vector by a scalar is a vector of a variable size. Let me give you an exact spot where we have already done this. Sum of forces equals mass times acceleration. If acceleration is this, okay, and mass is 2 kilograms, mass is a scalar. So what is, and let's say acceleration is, I don't know, let's go 3 meters per second at, it looks to be squared at about 30 degrees. So How do we figure out what force is? It's the scalar times the vector. So what does that do? It literally just changes the magnitude. We just take that scalar and multiply, and you would get 6. You'd, of course, combine units, kilograms, meters per second squared, otherwise known as newtons. But what effect does that have on the angle? None whatsoever, which makes sense because the net force is in the exact same direction as the acceleration. So net force in this case would be 6 newtons at 30 degrees. Same principle if I divide by a particular scalar. Obviously, I could take the opposite effect. I could say, hey, what if I take this exact same force, right? But instead of having a mass of 2 kilograms, I had a mass of 3 kilograms. Would it accelerate the same amount? No, it's only going to accelerate at 2. It's going to accelerate less because mass represents the object's inertia. The more inertia it has, less acceleration. It's going to have less change, and that whole same sort of thing. But that gives you hopefully a representation of those scalar principles. All right, component vector addition. Graphical vector addition is not recommended when you have high accuracy or if you have a 3-dimensional problem. So I will probably pause at the 3-dimensional part because we have definitely not done that before. All right, told you I would skip this, I'm skipping it. Ooh, I'm not skipping one part. Okay, so I do need to address something here. Components of a vector, you're good. That's a y, that's ax. This is just trig. This is literally what they did earlier when they went from polar to Cartesian. Excuse me, and Cartesian back. Although technically, when they were doing polar and Cartesian earlier, they were talking about single points, but the math does work out exactly the same way. So you can see mathematically it makes sense to draw these in a right triangle, but I will tell you that as you understand these a little bit better, what makes probably a little bit more sense, are they going to do it here, is actually drawing it like this instead. Because it's the same thing, right? Because as we said earlier, you can take a vector and you can move it wherever you want as long as it stays the same size and in the same direction, right? So this is still the same as this right over here, and you would still calculate it the exact same way, but there's benefits to doing that. All right, so I said I was going to skip components, and I did. There's the component conversation. Split it into the parts, find all the parts with trig. Once you have all the parts with trig, add up all of those parts to get the total, take the, and if you want to go back the opposite direction, there you go. Components, this is just generally what are the quadrants and what are the signs. Let's talk unit vector, which is the same and different, and yeah. What is the unit vector? Well, the unit vector, as it says right there, has the dimensions of the vector with the magnitude of exactly 1. The unit vector are used to specify direction and have absolutely no other significance. With the unit vector, this unit vector alone, by itself, tells what the direction is. But instead of doing it with angle, it simply does it with trig. So essentially, and maybe they're going to do this on the next slide, but if they're not, I want to show it real quick. Yeah, I don't like the way they present that, but I'm going to do my own way real fast, and then I'll show you their way, and I think it'll make more sense. So, in other words, if you had a vector A, okay, and I said, I want you to find this, that would be AX, right? And you would use, to get AX, you would take A and simply multiply by cosine of theta. Yes? So if you look at that, this piece alone, the cosine of theta, is all you technically need to specify what percentage of A is in that direction. For example, type in cosine of 70 into your calculator right now. What do you have?
I'm still switching to degrees.
Come on, let's go.
0.34.
What's that?
0.34.
0.34. Okay, Now, when you look at the definition of cosine right here, you see it's the ratio of x to r. Or if you think of r as the total, dividing by x essentially says 0.34 of that angle tells you 34% of the total is on the x-axis, right? So what we would do in this particular case is we would say that this is equal to the total magnitude times 0.34, and then we use the letter I to represent the unit vector. Does that make sense? So now, whatever my magnitude of A is, I'm still, because of this angle, this is specified the direction, right? And same thing for the Y. For the Y component is just going to be the total magnitude times, let's do 70 again. What's sine of 70? What's that? 0.66? And that one is typically used as j hat. So, in other words, if I wanted to say, what's that?
It's 0.93. I was
0.93. Okay, sorry. Which makes sense. It's going to be a lot. It's going to be in the y at 70 degrees. Okay, so what we would say here, and you'll see this in just a second, is that r, the total, is equal to a times the unit vector. And the unit vector in this particular case would be 0.34i plus 0.93 j hat. Does that make sense? Where actually this is, I could even specify further, that is the magnitude of A.
So is I hat always like x-axis?
Correct. I hat's x-axis, j hat's y-axis, and k hat is going to be z-axis. And yes, you will be dealing in 3 dimensions a little bit. So the other way to say this right here, and you'll see it in just a second. I'm trying to give you a numerical definition, kind of showing you kind of how stuff you already know plays here. But this, everything in parentheses, would be known as r hat, the unit vector. The key thing to get out of that is this. Anytime I put r up here, you have to remember that x and y are buried inside of it. Okay? So if I put r hat, and they're going to, in a lot of these definitions, you have to know that, what do I do with this? Well, x hat and y hat are buried inside of it. What happens on the x, what happens on the y are both inside of this, and I would usually do this mathematically by dealing with each of them individually. Let's keep going. Hopefully this helps a little bit. All right, so here it goes. The symbol of I hat and j hat and k hat, okay, represent the unit vectors. I goes with x, as you see right here in this picture. J always goes with y, and k always goes with z. The magnitude of each unit vector is always 1. So in other words, this is going in 3 dimensions right now. So in the example I just gave, watch here. Example I just gave, sorry Eleanor, this is a visual representation of holding a meter stick. Okay? If I took this and put this up 70 degrees, this would be the unit vector representing 1, right? Whatever size of this, we know that 93% of it is here and 34% of it is here if I'm holding it perfectly at 70 degrees, right? What they are doing, adding k in, is this. They are simply letting this thing rotate into the z-axis. Now notice, has the size of the unit vector changed? No, but probably what has changed a little bit, actually it might not have changed. As a matter of no, I don't think it has. The x percentage, it might have. X percentage actually probably did. The x percentage potentially changed a little bit here. The y probably didn't. I think it's about the same height. But obviously now there's a little bit in the z as well. But adding up all 3 of them gives us a unit of 1. All right, I'm moving on. So unit vector and standard notation. So we would say that a hat is equal to axi plus ayj. Now, what is meant by that? Well, I've actually already got this number nicely up there on the board, okay? You've done this already, but it looks a little bit different to you, so that's why I want to make sure and compare what you already have. So A hat, I already have on the board, but I'll write it up here for Eleanor. 10 meters at 53.1 degrees. That's that. And that is equal to 4 meters x at 5. Sorry, nope, that's wrong. That's wrong. That's wrong. Darn it. It should be 3 meters. That's the only thing that's wrong. Because this is a basic triangle, is how I knew that, or you could have done trig to figure this out as well. So the main thing that's different here is simply, in all honesty, it's going to be the, excuse me, instead of the x hat here, it's relatively simple in that this is just the, sorry, screwed that up again, didn't I? Going too fast. J hat. There's some small discrepancies between those two, but for the most part, we're pretty good. All right. So positioning examples again. This is what I was saying a second ago. The r hat value, assuming that this is 1, is equal to just basically the I plus the x. Okay. This equation right here is literally what I was showing when I did this right over here. That everything inside this parenthesis is equal to r hat right there, right? So if you would take the r hat times the magnitude, that would tell you exactly what the original vector actually is. You in the right direction? Yeah. So, adding vectors using unit vectors, this looks super complicated, but it really isn't. All you're looking at up here is literally just component vector addition. Now, we write them right next to each other, but if you follow basic math principles of like terms, what are you going to add together? Well, I'm going to add everything on the x, everything on the x, and everything on the y, and everything on the y, which is literally what they're showing here. Add all the y's, and you can factor out the j. Add all the x's, you can factor out the I. Okay, and then your final is just going to be all of the x plus all of the y. All this is saying is something to the principle of this. If I told you that there was a vector of A in Cartesian form of plus 1 x hat minus 2 j hat, and then I told you that there was a vector of B of plus 3 x hat plus 3, sorry, I screwed up, my goodness, I'm irritated. I was doing x and y, and I should keep with x and y, but I'm mixing back and forth between x and there we go. What is the total final answer? That's literally what that tells you. Literally what this says right in here. So it's not any different. It looks different, but it's not different. Okay? And then finally, all right, so you've got AX and AY and all that. If you want to get it into polar, this is exactly what you've done before. Yes? Adding vectors with unit vectors, it just means what you can essentially do is pretty much the exact same thing. You add the AX, you add the BX, and this is just showing you visually what was on the last page, right? That, or I can use my numbers to do the exact same thing. 1x negative 2y. There was my first vector. I called that A, and then 3 and 3. There was my second one. So what is R is all that's happening. You did 1 and 2, and 3 and 3, and you ended up with a total of 4x, 1y, 4x, 1y. Yes? All right. Moving on. What happens if we have 3 dimensions? Well, the great news is, component-wise, it's pretty much just do it again with the k side as well. Combine all the i's, combine all the j's, combine all the k's. Great. Now, what do I do when I switch to polar? Well, here's the good news. Okay, in the example I showed you earlier, Eleanor, once again, I'm holding the meter stick, where I was just in the x and the y, you very easily know how to find the magnitude of this. Yes, it's just Pythagorean theorem, right? Now, watch what happens, though. Okay, watch what happens, though, when I shift out here. Okay, well, what I can do is, my apologies for attempting 3-dimensional stuff right now. This is first quadrant for you, yes? It's backwards for me, I apologize. Yeah, first quadrant and actually arguably first out of, sorry, 8 quadrants. But anyway, what is it, cubans? I can't remember. Anyway, so if I take the x and I take the y, look at what I'm doing here, okay? If I take the x and I take the y, what I have is I can get an r value out of that. If you think about this carefully, that r value that I just drew, by definition, in this plane, okay, here, I will draw that. We got an x, you've got a y, okay? By definition, which way is the z from there? From this particular picture I've drawn, which way is z? Straight out at you, right? So, to show you that, is r at a 90-degree angle with the z-axis? So could you still use Pythagorean theorem again for that triangle? Yes. So arguably what you're doing here is you're finding r, which is equal to the square root of x squared plus y squared. And then the z-axis that comes out right here is at 90 degrees to that. So to get this vector here, Eleanor, I'm pointing out in 3 dimensions, so it's hard for me to draw this. I'm going to get by basically doing Pythagorean theorem again with the z. But it would be r squared plus z squared square root. Yes? Now, if I take these two, though, and put them together, what you'll see is that r squared is the square root of x squared plus y squared squared, right? Plus z squared square root, which simplifies to, what is this square to the square root? So we have the square root of simply x squared plus y squared plus z squared. So technically what we're doing is Pythagorean theorem twice, but you can see numerically that actually simplifies out to just put everything underneath the square root. And you get this guy right here. Yes? Now, polar is a pain in the butt, though, as far as this next thing is concerned. And then I'll answer your question. Okay? It's showing you this, theta of x. What that says is, and I'm holding the meter stick right now in 3 dimensions, what that says is that this line from the x-axis, you could shift up a certain amount of degrees. To find that, we could take the x component right here, the total x component of r, and divide by the total r that we just found with that kind of exorbitant Pythagorean theorem done twice situation. And that will give us the angle from the x-axis. The problem is that's not fully going to describe where the vector is. It'll only describe how much angle is between the x-axis and up. But I'm going to need 2 angles in order to use polar to describe where something's at in 3-dimensional space. Now the good news is finding either of the other 2 angles, you only need one other. But it's the exact same equation, except basically you're going to use the appropriate exponent in that particular case. Does that make sense? So I would find theta y. Ooh, but is it cosine or is it sine? Let me think of this. Okay. So this would be, I usually want to do z actually, not that. That's actually a good indication though. Okay, so if I want to get z, the theta with respect to z, so this would be the z-axis here. So the z-axis here would be shifted up right there. So I want to get the z component the z component here relative to r. Yeah, it's cosine. It's still cosine. So it's still cosine. The only difference is that now it's the rz component compared to r. What I just described to you took me a really hot second to sit down and think through. And obviously you saw me just do it right now. I have to rethink of it every single time. And I don't think I fully, like if I was really trying to do a problem like this, I'm sitting there for probably about 10 minutes just to make sure I'm on the right page when you start working with some of this stuff. Adding 3 or more vectors in 3 dimensions is, once again, just add the other ones, just add more x's, more i's, more j's, more k's, more x's, more y's, more z's. I'm done with vectors, I'm pretty sure. Make sure that we're good. There's nothing I want to cover. Cool. Score. Questions on any of that? Yes?
So when you say that the z-axis is perpendicular, you say it's perpendicular to the r?
So the z-axis, okay, here we go. Good question. All right, watch this. I'm going to swing this all the way around, representing a vector in any particular spot. Okay, if you'll notice, as this thing sweeps around, it makes what's known as a plane. Okay, a plane being a 2-dimensional sheet represented by 2 dimensions, x and y. Right. So in other words, I could spread out. Now we haven't had to worry about planes pretty much yet because everything we have always done has kept in 2 dimensions, not 3. So what you got to remember is the z-axis is perpendicular to that entire plane. Right? Like, in other words, if I have z-axis for you guys is straight at you, right? So if I say this is my plane and that's my z-axis, no matter where I put this, notice that this vector is 90 degrees to the z-axis. Does that make sense? Okay, so it's to that entire plane. Or you could think of it like this. I mean, it's symmetrical. It's a 3-dimensional version of symmetrical. But like, you could do it this way. You could do it this way. Instead of doing my plane as your standard x, y, and making the z the weird one, now I could do this. Okay. Now I've made a plane out of which 2 axes? Y and z. And you'll notice everything along the x runs parallel to them. Right? So this was, by the way, this was x and y. Okay. This was x and z, so y and z, hold on, what I did, x and y, I did y and z, so I need to do x and z, oh, it's this one, so I don't like, right, so if I do x and z, then the y dimension is entirely, so they're 3-dimensionally symmetrical, whatever that word is. It's messy, I know. Yes.
In that case, would you do like the Pythagorean theorem of 1, and then would you do like that by itself?
That's what I was trying to show you. What I was trying to show you is that technically what you're always doing is Pythagorean theorem twice, right? But it always works this way in case you want to do it like this. Sure, you can do it twice. If you want to do it like this, you do, like if I want a vector like over here, I would see that this vector is moving in the x, is moving in the y, and is moving in the z. I could make a triangle out of the x, which is currently negative, okay, and the z, which is currently positive. And you can see that kind of triangle represented right here, right? Hold on, I wanted to do it like this, okay, represented right here. But if I shift this up, this triangle is still the same, but the y is now 90 degrees to that. So what I'm doing is, I'm going to try to show this with my hands, it's not great. But I use technically the Pythagorean theorem along the x and along the y in order to find, watch this, I do it to find r. This is r for those 2 vectors, right? Now notice that r is the base of this triangle right here. So I use x and y to get r, and then I use r and z to get the magnitude of this one. But what I tried to show mathematically up here for you is that I'm trying to get you to skip to the shortcut, but you do need to understand where it comes from. And that was on, where was it? Oh, I erased all those. This one, okay. So what I did was so what I just said was take the x and the z and square them. So you would have whatever vector, we'll call it a, ax squared plus az squared gives me r. Right? That's what gives me this r right here. So how would I find the magnitude of this? I do Pythagorean theorem again, which would be r squared, because that's now the base, and the height would be a y squared. And this would give me the actual total magnitude of it. So, but what I try to then show is that if you look at this, r being plugged in here simplifies out to just this. That way you can do it in one step. Technically, again, what you're doing there is you're doing the Pythagorean theorem twice, but this allows you to do Pythagorean theorem twice much quicker. Shut up.
Talking about your hair color.
Great.
Was it gray last year?
Yes.
But as much, you think?
I mean, it's getting more gray. It's kind of how time works. But if you're talking about reference to my child causing it, no, I don't believe
That's not what I said.
Oh, okay. What did you say?
Well,
I heard the child.
And a child.
And sure. The main thing is my family gets gray early. My uncle is entirely gray by 30 years old.
Looks gray already.
He's not. But my uncle, like I said, 30 Spain hours go gray super early. My dad was gray. My uncle was. What's funny?
Well, because you said Spain hours.
Yeah.
But to us, your Spain hours.
There's many of us.
There's many of y'all.
He has been cloned.
All right. Chapter 4. I didn't even go as fast as I probably should have on the last one. I'm going to try to go even faster here, and I'm going to try to let you guys kind of figure it out as you start to work on the homework, because I think that's truly where you're going to see some of this stuff shine. So let's go. Greater detail. Okay, here is the main thing to get out of this slide. Two-dimensional kinematics. Technically, circular motion is two-dimensional. They are going to start with circular motion way sooner in calculus than we ever did back in forces. Okay, so luckily you got that under your belt, so you might see some of that stuff today. But if you think about it, circular motion is in fact a form of two-dimensional kinematics. Yes, so there's two forms of two-dimensional kinematics that you're going to see in this chapter. What you're used to from last year is just saying 2D kinematics, projectile motion. Okay, now what I'm saying is that 2D kinematics could either be projectile motion or circular motion. Do you remember what the major difference is in the cause?
The force.
Force
Close.
is completely perpendicular in circular motion. Or acceleration is perpendicular.
Close. Draw a sketch of perpendicular motion, projectile motion on your page, and then do here you go. Projectile motion with an object shot horizontally, and then just do circular motion and draw the vectors at two separate times, and I think you'll see what I'm looking for. And maybe you already saw it, but I want to. So, projectile motion. Circular motion. Draw them at two times. Now the key thing here is the accelerations. What's the difference between the accelerations in both motions? In projectile motion, what happens with acceleration? It stays in the same direction the entire time. Whereas in circular motion, acceleration, for whatever reason, stays perpendicular to the to the velocity. So that's the major difference. In projectile motion, acceleration stays pointed in the same direction for whatever context. Easiest one for context is, of course, gravity stays pointed down. It doesn't, but for our particular point of view, in a limited spot, it does. So there you get projectile motion. If for some reason, like, a kid wrapping around a pole at the playground, right? Kid holds onto the pole and swings around. You can see because of their arm changes its direction of force, changes the direction of acceleration. It stays perpendicular. Since it stays perpendicular, we get circular motion and not projectile motion. Does that make sense? Or think of it like this. Projectile motion is when we look at gravity from the perspective of a very small distance. When was gravity used for circular motion? When you go actually zoom out, because we see that actually gravity does change direction to stay at 90 degrees, and thus as it does that, it's going to be in circular motion instead of projectile. All right, so is anything really in projectile motion? No, but we'll assume that. All right, so this is the beginning thing, and the reason I spent probably so much time on the vectors over there is to understand this particular guy right here. Okay, ignore for a second Ri and Rf. Okay, Ri and Rf represent just where it's at. Okay, they're a vector to represent displacement, or actually Ri and Rf are vectors to represent initial and final positions. Okay, where is Ri? It's this spot right here. So just ignore that arrow. Okay, that arrow is just a point right here to tell you we start here. Okay, what is Rf? The arrow to point here. So what is delta R? Simply a displacement. Just rather than displacement going in the x, we would call delta x, rather than displacement entirely being in the y, we see it has both, so we would call that R. Why do we say change in R? R represents position. And what's displacement?
Change in position.
So it's the change in these two particular vectors. Now, as I said in the last section, when you see R, what should you think? X and Y are buried inside. Okay? So anytime, so X and Y are here. Okay? If you wanted to think about it more basically, here you go. All we're saying is Ri, well, that has an X right here. Right? Rf, that has an X right here. So what is delta X? Right there. You're very familiar with that, yes? Okay, and Ri has a Y right here. Rf has a Y right there. That is the change in Y. So Ri is equal to X plus Y, component vector addition. So just those two. Rf is equal to, no, sorry, that was supposed to be an I, and that was supposed to be an I, j hat. This is going to be confusing for you. It's confusing for me. And final piece is, what is delta R equal to? Delta R is simply equal to the Do you see what I'm trying to get you guys to see here? Okay, fine, move on. Okay, so general motion ideas. 2 or 3 dimensional kinematics, everything is the same as 1 dimensional, except now we just have to use full vector notation. So unlike last year where I said, hey, we did 1 dimensional, now let's just do 2. Okay, basically for calculus and a little bit for algebra 2, we're skipping forward into multiple dimensional analysis, but it's just the exact same thing. We realize that what we do in the x and what we do in the y work the exact same way, so what we do in the j will also, x, y, and z will also have that same sort of effect. I don't want to cancel at all. Cancel this process. I guess keep. All right, from current slide. So, as it says, positive and negative signs are no longer sufficient to determine direction because it's not one-dimensional. So, here we go. Average velocity. Average velocity, instead of saying delta x, is simply delta r over delta t. Okay? Meaning, if I start in 3-dimensional space, I'm pointing to spots here. Okay, right here. Actually, let's use tiles so this is nice for you. Okay? So, x and y are here. X and y are here. X, Y, and Z are here. X, Y, and Z are here. Got me? So what is the displacement? So this is initial and this is final. What is the displacement? It is an arrow pointing from here to there. Right? Okay. So if I want average velocity, all I do is take what I always did. I take the total displacement and divide by how much time it took.
Yeah.
Make sense? Same thing's going on here. Okay? So like, if I take this 1 meter to represent what I was just talking about. Okay, so here's 1 meter. Say it takes 2 seconds to go from over here to over here. What's my average velocity? It would be 0.5 meters per second plus the unit vector that's giving me the direction. So this is r. Okay, this is r, which my representation, the r, change in r, is equal to change in x plus change in y plus change in z. But these are all vectors. So you have to remember that even though I'm putting that positive sign, how do you technically add these? Pythagorean theorem, inverse tangent, all that fun jazz. It's not just standard addition. Yes, if you want to go from polar to the like. Okay? So what this says is if you want the velocity, it's that whole vector divided by t. So what I said is say it's a meter, it takes 2 seconds. So that's 50 centimeters a second, or 0.5 meters per second. Okay? The only difference is we have to add in the, we have to add in the unit vector. Or, another way to say that is we could take each individual component and divide it by time. So the change in r over the change in t is equal to the x over t plus the y over t plus the change in z over delta t. Yes, sir?
So, whenever you were talking about the Pythagorean theorem and the tangent stuff, like, so the change in r is equal to like the square root of all that stuff. It's not actually added. Is what you were saying, right?
Well, okay, whenever you see vectors and you see added, yes to what you said.
Sure.
But when you say actually added, what you're really saying is, because I want to get this definition right, you're not scalarly adding them like you're used to in math class. Anytime you see that positive sign and you see, so like if you saw this, you know, a plus b plus c, you'd go, oh, that's addition. Those are scalars. But if I said that exact same thing on the page, you go, that's vector addition, because those are vectors, and I'm adding those, so I have to keep in mind, yes, that is not what you're probably used to. Yes, sure. All right. So, how do I get instantaneous velocity now? Well, let's just deal 2 dimensions right now. 3 dimensions is icky. Okay. So what we see right here is this. Okay. If A and B, okay, would give us the average velocity to move right along here and divide by time to get the average velocity. What if I wanted the instantaneous velocity? Now you sort of already knew this, because if I drew projectile motion and had you figure out where the heck that direction, what's the velocity at that particular point, I'm pretty sure all of you can draw the correct line to tell me what direction it's headed in. Yes? What is that line called? Tangent, correct. The velocity is tangent at that particular point. Now the big difference here in this particular representation is this, okay? Is that we usually draw x versus t. Yes, for this graph, and I draw something like this. The one I drew over here is not x versus t, it's y versus x. Yes? Okay, so when I draw x versus t on definition, the tangent line is the velocity at that particular time. Yes? And is defined as velocity is the limit as delta t approaches 0 of the average velocity delta x over delta t that gets redefined as dx dt. Okay? That is when we dealt with it in 1 dimension. But you have to recognize that even though I drew the same shape Those are not the same circumstances, right? What's going on here, what's specifically going on here is that if you want to think about this mathematically, the t function is changing according to the second power. The x function is changing according to the first, okay? Which you will see in that equation right there. I'm sorry, I said that backwards. I said that entirely backwards. My apologies. The x value is actually changing according to the second power, and the t value is changing according to the first. Here, what is changing according to the second power in y versus x? The y. Okay? How come? Because it's the y equals 1/2 acceleration y delta t squared. In other words, there's acceleration in the y direction, so we use that particular equation. But the x is changing according to the first. Why? Because what happens to the velocity in the x direction in projectile motion? It stays constant. And thus, you use this equation. Sorry, I'm shorthanding this. But you can see this one changes according to the second power of time, and this one changes according to the first. Meaning, what you're dealing with here is 3 different variables, y, and x, and t. Yes? Now you can still use, as they said at the very beginning, basically you do everything in the x and everything in the y independently, and you can combine them together at the end. But what they're showing right here is that when we're comparing y and we're comparing x, we have to say r, because what's inside of r? Both x and y at the same time, which is what's happening to both of them at the same time, which is why this notation is 100% necessary. As a matter of fact, if we add the z-axis to it, we can still keep this exact same definition. And what do? Look, I take the derivative with respect to r. We know that, and you see this from right over here, at r, at the spot of r, which way is this thing going to be going? Tangent. Okay, we know, so I can take this, the derivative with respect to r. Yes? And how do I get r? R is simply going to be that vector at that particular point in time. That vector could be r, could be represented as 8x plus 3y. According to that, watch this, the velocity at that particular point would be, x hat rather. Velocity at that particular point in time would be 0, as opposed to this.
So the x hats are just like, they aren't even units. They're just like kind of.
They're placeholders. They're directions.
Yeah.
They're simply the directions. They're saying, hey, I'm dealing with the x. I'm dealing with your y. How do I get this? I would take the derivative, the d dt of 8x hat plus 3ty hat. And what would happen? Well, you know common notation. Can you distribute to both of those? Sure. 8x is just a constant. It's a position. So according to this function, nothing's changing on the position. Now, what equations do we typically use? What are the standard methods to use? Well, the typical locations, sure, for right now, we'll keep it. The typical notation to use, sorry, Eleanor, are, of course, what equation, so I just said, I'm going to take ddt of r in order to get, by definition, the instantaneous velocity at the spot of r. How is r typically determined? Well, inside r is both x and y's position. How do we typically determine x's position in projectile motion? Yes? So just give me a velocity in the x just to make up something real quick. 5. Okay, and how do we typically determine, by the way, technically, hold on, let's do this. I like this. Eraser, let's go back quick. Remember, so we're using our correct notation. Let's do this. Give me a different position other than 0. Okay, 2 meters. Okay. This would have an x hat around it, because that's what takes place in the x, right? And how do we get position in the y? Oops, screwed up. Now I'm going to make our lives. Let's give me a height that we're going to hold this at. 12 it is. It's a high. All right. Okay, let's say we drop it, so that goes to 0, right? And sure. And then acceleration is. Let's use another planet other than ours, just so that I can make some numbers nice here. Instead of negative g, we'll say we're on a planet that has an acceleration of 20 meters per second squared down. Okay, so that would be, of course, 1/2 of that would be -10. Oops, negative, not equals. T squared, and all that would be y hat. Okay, so this looks way more complicated than it actually is, but watch this. Okay, so how do we get the velocity at a particular point? We take the derivative with respect to r. What is r? Okay, the r vector is equal to the x vector. Sorry, no, it shouldn't be vector, it should actually be position. The r position is equal to x plus y. We just said x, it's this right here. So r is equal to 2 meters plus 5 meters per second t x hat, right? Plus the y, which the y is equal to plus 12 meters minus 10 meters per second squared t squared y hat. Now, I can separate all these different pieces out. This would be 2 meters x hat plus 5 meters per second t x hat, excuse me, plus 12 meters y hat minus 10 meters per second t squared y hat. And how do I get velocity? Velocity is equal to the derivative of this function. This is r. So we take d dt of this whole thing. So, what's the derivative of this is constant? 0. What's the derivative of that?
5 meters.
X hat. Okay? Do we know that it's traveling at 5 meters per second in the x? Yeah, we do, and it's going constant, which just makes sense then why there's not a t next to it to change how much velocity it is. It's staying constant. Then we come over here. 0, of course. Okay? Derivative over there. Times t. So this is our velocity. Notice, by the way, are both of these vectors? Yeah. So could you just add them like normal numbers? No. How would you have to add them? Vector addition, which makes sense because what we're saying here is in the x, it's going to stay at a solid 5. Right? And in the y, it's going to change. Oops, sorry, I screwed this up. It's going to change by 20 meters per second every second. What did I tell you the acceleration was on this planet?
20 meters per second.
So how fast should it be going in the y in 1 second?
20 meters per second.
How fast should it be going in 2 seconds?
40.
So let's say we evaluate this at t equals 2 seconds. That is not going to change. I plug a 2 in here. So I have that my velocity at this time is 5 meters per second x hat minus 40 meters per second y hat, which just says it's traveling in the x5 and it's going in the y40. And if I really wanted to find the polar form of this, what would I do with these two? Pythagorean theorem and inverse tangent. Make sense? Okay. So notation is a little bit different, but math stays pretty much the same. Let's go quicker. So direction of instantaneous velocity at any point of the particle path. Again, tangent. Tangent to the path at that point and in the direction of motion. Speed is the scalar quantity. We've talked about this. average acceleration. This is the old average, well, no, it's not the old average acceleration. It's just the acceleration again. Except now you have to remember that each of those velocities has components buried inside it. You saw on the last one, you saw on the slide I just said that the final velocity, or the velocity of it at that particular time, was 5 meters per second minus 40 meters per second, x hat, minus 40 meters per second y hat. This would be that right there, right? What would the initial velocity have been in that last problem I just gave you? And that's it. So then, when you would subtract this guy from that, which is just 5 meters per second x hat, what will you notice about the change in the x? It hasn't changed. It will cancel entirely out. What will the change in the y be? Just this negative 40 that particular time, which makes really good sense on that particular condition. It really becomes helpful, of course, when we don't deal with projectile motion in its standard form of just it's constant in the x and constant in the y. But what if we have wind now? What if we have wind in a different direction? Well, now, does a ball that is thrown in baseball always go at a constant velocity in the x? No. But if I have a function to determine the force and direction of that wind, I can compare it to the forces that already exist in gravity and work my way backwards and calculate exactly where a ball is going to be in a much more accurate capacity than we used to. So average acceleration right here is as you're looking at right there. If I look at the velocity at A and the velocity at B, notice once again we're on the picture of y versus x right now. So you'll notice both velocity vectors are tangent to their respective paths at that particular point, which doesn't inherently mean tangent to the r vector, by the way. But as always, average velocity is defined as the change. You write the final minus the initial, or add a negative vector, and you get that guy right there. So according to this, what's the direction of acceleration? Down and to the left. So according to this particular picture, you should be able to answer me this. If the ball is originally traveling upward, is it speeding up or slowing down in the y? Slowing down. At point A, let's say that's the top. It's not exactly. Let's say it's the A. What is the ball about to do in the y? It's about to speed up in the negative direction. Okay. What is the ball's velocity doing in the x? It is slowing down in the x, which you can see because the component of the change in velocity is in the negative x direction, opposite of the direction of the velocity the entire time. Or another way to say that is if you looked at this x component and this x component, you should have noticed that my second arrow that I just drew is in fact smaller, and thus the x is in fact slowing down. Cool. So this is instantaneous acceleration. I'm not going to go too much further into this because it's the same process by which if you have the velocity vector, aka if I go back to my last slide where I developed a velocity equation right here. This was the velocity at t equals 2, but this was the generic velocity equation. What do I do to that equation to find acceleration? Derivatives, and the derivative of a constant is going to be to 0, and the derivative of that constant is going to be negative 20 meters per second y hat, which is exactly what I told you was the acceleration of the planet at the very beginning. Okay? So what does this mean is potentially going to happen on like weird or different planets? We are potentially going to have to deal with functions that do not have a constant velocity in the x, and those are easily represented by basic derivative forms. It's just this. When you step up into difficult content, there is this danger, okay? And the danger is to you can go down either rabbit hole and neither one is good. The first rabbit hole is this. You just deal in function. You go, hey, this happens all the time in calculus. And I know that Lauschke yells about this probably in a slightly different way than I do. But what will happen is everybody gets really good at antiderivatives, but they don't know what's actually going on under the hood. So if something throws a hook and it's not quite the same, you can't use the standard stuff, and everybody goes up in arms and throws their hands in the air and goes, I have no idea how to do this problem. Then you didn't know how to do any problem, right? You didn't actually know, you just knew the trick. If you only know the trick on how to get the derivative, right? If you only know that the derivative rule is 2x squared, multiply the exponent out front so I can get 4, subtract 1 so it's 4x. If that's all you know and you don't know the limit form of derivative, the moment things step up in difficulty, you're going to struggle hard and not entirely know what's going on. That's why it's so important to know what's going on underneath the hood. Same sort of thing here, okay? It's not a bad spot to start in function. You guys know how to do derivatives. I was trying to make connections to from these concepts to stuff that you very well know, that I know that you know, okay, both in the form of calculus and in the form of what we've done in here in projectile motion. But make sure you're looking under the hood at the same time, and that kind of takes to you, because you can 100% use all the tricks and finish the homework and like, yay, and even possibly score decently on the test, but do you actually know what's going on? I don't know, that's up to you, okay? And if you don't do that, that's where things get a little bit tricky if you go any steps further. The rule I've always said is the moment you take the shortcut and don't know what's going on underneath the hood, that's the furthest you get to go. That's the furthest you will understand stuff. Because beyond that point, if you don't know what's actually going on, everything has to be a trick. Somebody has to tell you the trick on how to solve the problem. It's the thing that math teachers hate. It's the thing that math students oftentimes want. Just tell me how to do the problem. What do they really say? Just show me the trick. Just show me the thing I do, and I get the answer in the back of the book, and I turn it in, I get the homework done, and I get the grade. But if they don't know what's going on, this is why pre-calculus is such an important subject. Because a lot of people complain about pre-calc. It's the same thing. It's the same thing. It's the same thing. What are they trying to do in pre-calc? Well, here's what they used to do. They used to have pre-calc. Juniors used to take calculus at Alton High. Okay? And the issue was that juniors taking calculus, even though they technically had all of the tricks to do the things, had no idea what was going on underneath the hood and sucked at calculus something fierce. So it took them 2 years to teach calculus, and they didn't get as far as you guys get now in 1 year. Why? Because they didn't actually know what was going on. They just knew the tricks. And there's a difference between that. It's what I yelled about a little bit before, in the form of, if you've ever heard me complain about NOVA special understanding. A student goes and watches a documentary on special relativity. They watch it for 30 minutes, and they see some cool tricks that they talk about on special relativity. Then they come to my class, and I say, I'm going to talk about special relativity today. And that student says, I know special relativity. Do they? I'm not trying to be, patronizing. I'm trying to be patronizing here. I don't think that they do. I don't really think that they understand it. It's the same type of thing to deal with potentially in math. All right, so we talked about this already. We talked about instantaneous velocity. Producing an acceleration. You know how to produce an acceleration. How do you produce an acceleration? Nope, that's not how you produce one. That's not how you make one. How do you create a force? Be careful. Be careful, and I don't think the text right here is actually doing a great job of this, because I don't like producing acceleration said in this particular way, okay? But they are talking about direction, which they're about to head into. I think talking about circular motion here in just a second. Yeah, no, they're going to talk about kinematic equations. But, excuse me, cause and effect. Acceleration that we have been dealing with, kinematics, is only effect. Okay? Everything you did on one-dimensional kinematics is me saying, like, hey, these are the conditions that it's in, what happened because of it. We're looking at entirely results. Cause is an entirely different chapter. There's nothing in this. Changing velocity does not cause acceleration. That's what I'm looking for here. Acceleration causes velocity to change. What causes acceleration? Step back to force. Correct. All right. This is just the kinematic equations, but we will run through these again. Ooh, I don't love that. Then we'll talk about circular motion. Period, you know. Tangent acceleration and centripetal acceleration. There's relative velocity conversation again. So again, a lot of review, except for that guy's definitely not review. So there's 3 main topics to cover left, and that is the kinematic equations in the form of calculus for algebra, kinematic equations. And as you saw, I will talk circular motion again quickly. But the good news about circular motion is it's the same thing. It's just pretty much one equation for the most part. It's going to be, where'd it go? There you go. That guy right there. That guy right there. We're not even going to deal with angular velocity yet. So yeah. So we have to talk about equations, circular motion, and we have to talk about relative velocity. I think that conversation will take me about a half an hour to an hour on Monday, and we'll be all done with the new stuff. Anyway. Once again, similar to last chapter, a bulk of your work in this chapter, a bulk of what's going to like really grow you, sadly not the lecture that I'm doing up here tomorrow morning for that, but it's going to come out of just doing the work in the homework. Start the homework early. Start the homework early, as always. How did that go? All right, I'm done. Bye, Eleanor. It was real. Oh, this is helpful for you. It's for that lecture at the end. I just got to talk.